Welcome to SS2 Computer Science, Term 3, Week 6. Every algorithm takes time to run and uses memory. As the input size grows, how does the running time and memory use grow? This is what complexity analysis measures. BECE notation is the standard mathematical language for describing algorithm efficiency. Understanding BECE is essential for choosing the right algorithm and writing efficient code. By the end of this lesson, you will define time and space complexity, read and write BECE notation, classify common complexity classes, analyze simple algorithms for their complexity, and compare algorithms using BECE notation. Let us begin. Why do we need complexity analysis? Consider this scenario: you write two programs that both solve the same problem. Program A takes 10 minutes for 1000 data items. Program B takes 0.01 seconds for 1000 items. Which is better? Clearly Program B. But what happens with 1 million items? Program A might take days, Program B might take a few seconds, or it might take hours if it grows differently. Complexity analysis lets us predict how an algorithm's performance scales with input size without running it on every possible input. Two types of complexity: time complexity, how long does the algorithm take as a function of input size n. Space complexity, how much memory does the algorithm use as a function of n. We measure complexity in terms of the number of basic operations performed, not actual seconds. Seconds depend on hardware, language, and other factors. What is n? N is the size of the input. For a certain algorithm, n is the number of elements. For a search algorithm, n is the number of elements in the dataset. For a string algorithm, n is the length of the string. For a graph algorithm, n might be the number of nodes or edges. What is BECE notation? BECE notation describes an upper bound on the growth rate of the number of operations. We say an algorithm is O, F, n, if, for large enough n, the running time grows no faster than f, n, times some constant. Informally, O, F, n tells you the worst-case growth rate. How does the algorithm perform as n grows very large? We drop constants and lower order terms. Instead of 2n superscript 2 plus 5n plus 100 operations, we write O, n superscript 2. The constants and lower terms become insignificant as n grows. The common complexity classes from fastest to slowest growth: O1, constant time. The algorithm always takes the same time regardless of input size. Example, accessing an array element by index. ARR is always one operation, returning the first element of a linked list. Return head.data, hash table lookup, average case. O log n, logarithmic time. The algorithm reduces the problem size by a constant factor each step, typically having, example, binary search. Each step eliminates half the remaining elements. For n equals 1, 0, 0, 0, 0, 0, 0, only 20 steps needed, grows very slowly. O n, linear time. Time grows proportionally with input size. Example, linear search, check each element once, reading through an entire array once. O n log n, linearithmic time, slightly worse than linear. Example, merge sort, quick sort, average, heap sort, efficient sorting algorithms. O n superscript 2, quadratic time. Time grows as the square of input size. Doubling n makes the algorithm 4 times slower. Example, bubble sort, selection sort, insertion sort. Worst case, nested loops each going 0 to n, O, 2 to the power of n. Exponential time. Time doubles with each additional input element, grows extremely fast. Example, recursive solution to the Tower of Hanoi. Brute force password cracking, checking all combinations, solving the traveling salesman problem, brute force. O n. Factorial time, grows even faster than exponential. Example, generating all permutations of n items, completely impractical for n greater than 15. Growth rate comparison: n equals 100. O 1 equals 1 operation. O log 100 is almost equal to 7. O 100 equals 100. O 100 log 100 is almost equal to 700. O 100 superscript 2 equals 10,000. or 2 to the power of 100 equals a number with 30 digits, completely impractical. Rules for analyzing BECE. Rule 1, constants are dropped. An algorithm that does 5n operations is O(n), not O(5n). 100 operations is O(1), not O(100). Rule 2, lower order terms are dropped. N superscript 2 plus n plus 100 is n superscript 2, because for large n, n superscript 2 dominates. Rule 3, for nested loops, multiply the complexities. Outer loop n times inner loop n times equals n superscript 2. Rule 4, for sequential operations, add but drop lower terms n plus n superscript 2 equals n superscript 2. Worked examples. Example 1, for I in range, n print, where 1 loop, n iterations, O1, work each n. Example 2, for I in range, n for j in range, n print, where plus AR, 2 nested loops each 0 to n superscript 2. Example 3, for I in range, n print, I n, result equals AR, O1, total equals n plus O1 equals n. Example 4, binary search, loop runs while low equals high, each iteration, low equals mid plus 1 or high equals mid, 1 halves the range. How many times can we have n before reaching 1? That is log 2, n, times O, log n. Example 5, merge sort, divide in half, log n levels, at each level, merge all n elements n log n. Analyzing space complexity, O1, space, in-place algorithms, bubble sort, binary search iterative, use fixed amount of extra memory regardless of n space, merge sort, needs extra array of size n to merge, storing a copy of the input. Log n, space, binary search recursive, call stack depth is log n. Best, average, and worst case. Best case, algorithm's performance on the most favorable input, typically O1 or n for search. Average case, expected performance on random input, quicksort is n log n average. Worst case, algorithm's performance on the most unfavorable input, most important for guarantees, quicksort worst case n superscript 2. Practical guide, which algorithm to choose. You have n equals 10 million items to sort, n superscript 2, sort, bubble sort, would require 10 superscript 1 operations, would take days even on a fast computer, n log n, sort, merge / quicksort, would require 2.3 times 10 operations, completes in seconds. You want to search a sorted list 1000 times, sorting once, n log n acceptable cost, then 1000 times log n binary searches, very fast, versus 1000 times n linear searches, much slower for large n real-world significance. Google's search engine must handle billions of queries, every millisecond matters. Choosing n log n versus n superscript 2 algorithms is critical at this scale. Memory constraints matter too. On an embedded device with limited memory, an n space algorithm may fail where an O1 space algorithm works. WAEC questions on BECE. State the time complexity of bubble sort. State the time complexity of binary search. What does n log n mean? Compare two given algorithms by their time complexity. Analyze a given pseudocode snippet and state its BECE time complexity. Explain what it means for an algorithm to be O1. Rank a list of complexities from most to least efficient. O1, log n, n log n, n superscript 2, 2 to the power of n, n. Key points. Complexity analysis measures how an algorithm's time and memory use grow with input size n. BECE notation describes the worst-case upper bound on growth rate. Drop constants and lower order terms. Common classes, from most to least efficient, O1, constant, array index, hash lookup, log n, logarithmic, binary search, n, linear search, n log n, linear arithmetic, merge sort, quick sort average, O, n superscript 2, quadratic, bubble selection insertion sort, O, 2 to the power of n, exponential, brute force combinatorial, O, n. Factorial, permutations. Analysis rules, single loop O, n, nested loops O, n superscript 2, having O, log n, divider merge O, n log n. Space complexity, O, 1, in place, O, n, extra array, O, log n, recursive call stack. Best/average/worst case. Worst case is most important for guarantees. Big O of algorithms we have studied: linear search O, n, binary search O, log n, bubble sort O, n superscript 2, worst, merge sort O, n log n, always, quick sort O, n log n, average, O, n superscript 2, worst. WAEC, state complexity, compare algorithms, rank complexities, analyze simple code snippets, explain why complexity matters.